Okay, I'm going back. Let me share again the screen. Um, 1 second. Okay. So we are going to do the draw test for the testing the breakpoints. So we will divide our data frame. No, let's do it this way. Okay, we already have our formula. Let's say 2008 quarter quarter end. Like this. So we will set breakpoint date as the end of quarter 2. And we divide our sample into 2 parts. Model 12. Then, so here we estimate a model on the full data set, then we estimate the, oops.
Excuse me, and what is a PD point offsets?
This is what I've been doing before. So let me show it. If you do it this way, then it gives you the beginning of quarter 1 or quarter 2. If you add the offsets quarter end, it would nope. Wait. How does it work? So it's the same that I was using. I need to use this. It's a function like this. It brings it to the end of the quarter, the date.
Yes,
So
okay.
quarter 3 would be July 1st, the beginning, and would be September 30th. Actually, let's do quarter. Well, we'll experiment. We'll experiment with quarter 2 and quarter 3. So before, yeah, before. After, then let's see, so far no problem. Then we can check the before. Oops. So it starts with 1997 quarter 2 and ends with 2008 quarter 3. And then the after starts with quarter 4 2008 and then ends with the end of our data quarter 4 2019. Perfect. So just to check that what we have is right, then we can see another full summary. So this is actually, we had it before. Let's compare it more before summary. So say coefficient is, let's say which one is important, this 0.29. Not that different, maybe different, but we'll do a statistical check. They doesn't seem to be that different, but we'll check the statistically all the coefficients simultaneously. So anyway, let's go back to the construction of the test. There is no standard show test in Python, but it's easy to write it on your own. Not for params, it's the number of regressors. You can see here these are the regressors, and they just take the 1, 2, 3, 4, 5. So k will be the number of regressors. Then this is a full sum of squared errors is full sum of squared errors. Sum uh-huh. And finally t the f will show 0. That's the size of t is the size of the sample, and this sum of squared residuals. Then actually, just to make sure, yeah, I don't need to do this sum. because it's already sum of squared residuals. Then numerator is equal to, for the FSR of 4 minus FSR of 4 minus FSR of 4 divided by K. The denominator is equal to FSR divided by K. And charge that is equal to just division of this on numerator and denominator, and then we also tells that this is tells that this fix break point. The statistics has under H0, which is this one. Let's say prime H0 double prime has the f k t minus distribution. So we use a statistical package to calculate the sci-fi stats CDF constant degrees of freedom K and DFT. So let's see. Bring this text. When let's see. Okay. So p-value is relatively high, but on the verge. So let us do. Basically, that's the Cho test. You calculate this ratio of residuals, sum of squared residuals. You can check it in the econometrics textbook. Usually, for some reason, there's no implementation in Python in standard libraries. So, but using our own implementation is very straightforward. So let us wrap it into a function. Um, let's do this. Okay, should work. Yeah, looks good. Okay, so now let's check quarter two. Similar, quarter four. So quarter four, we definitely reject, well, at 5% significance level, p-value. No, that's, sorry. At quarter three, p-value is on the verge. It's like low enough to reject. The probability is low enough to reject, at least at the 5% level, the hypothesis of stable coefficients. So here we were testing if the coefficients are stable before this global financial crisis or after. But of course, in order to find the breakpoints, we need to come up with some idea where the breakpoint can come from. And this is fine. We can do the Chow test. And so, like, using this Chow test, perhaps we would select the model. The model doesn't change, but the coefficient estimates change, and there is a structural break, so-called structural break in the coefficients, perhaps before the global financial crisis and after. We then can search for structural breaks more systematically using a recursive estimation approach. So there is this function which is, one second, the function.
So the Chow test showed us that if we put a breakpoint like the third quarter of 2008, then our coefficients, well, we reject the hypothesis that our coefficients before and after the breakpoints are the same.
No,
Right?
so that we see that the p-value is relatively low, at least at the 5% significance level, which means that the probability of H0 null hypothesis is somewhat low. And so perhaps this hypothesis is not the right one. Maybe the alternative hypothesis is, I mean, we cannot reject the alternative hypothesis at a factual confidence level.
So our coefficients are different if we apply this breakpoint, right?
Yes,
Okay.
right. And so the model somewhat changes. Now the question is what we can do with it, and we will get to that. But let me show another way of doing it. There is 1 second. Recursive. Yeah, this one. There is a recursive least squares, which would be estimating the model recursively on each data point and taking next data point, estimating the model, taking the next data point, estimating the model, and so doing this estimation in a rolling way. And then we can look at different tests. We can look at the estimated coefficients, and we can look at different tests. So let me first perform this, and then I will talk a bit about this. So mod recursive. Starts now, recursive ls. Yeah. So recursive ls, it requires endogenous, exogenous variables. So we need to specify, we cannot do it from formula. So we will do it so that would be our endogenous. And our exogenous is going to be CCI, ICI, confidence, IPI, and H, harmonized consumer price index. And does it include constant? Yes, we need to add constant. Actually, yeah, let's do this. No? Nope. Harmonized consumer price standard, how do I call it? Yeah, harmonized index of consumer prices. Okay. Perfect. We estimated this thing. And now, no, that we specify the model. Let's guess like this fit. And then what we can do, we can construct a couple of plots. The first plot is this. Recursive coefficients.
About exogenous and endogenous variables. So aren't they just dependent and independent variables in this context?
Yeah.
Okay.
By the way, is this confusing? This.
We just, well, in econometrics, we talked about endogenous and exogenous variables in the context of instruments. So exogenous variables are okay as they are, and endogenous variables, we should use some instruments.
Right. No, so here endogenous means dependent and dependent, right?
Yeah, okay.
But I was also asking if this notation is confusing or not. Like endog is equal to endog, exog.
It's just like first one, I guess, is the parameter, and another one is just the object which you made.
Perfect. This is a little fun thing that I like to do in Python. Now, okay, what's happening here? Let me see. Res not defined. This one is not defined. K exogenous. Hey, what's going on? Okay. Actually, I need both. Like this, and now it should work. Nope. Okay, finally. Let's do it larger. What's going on? Okay, I see. Okay, and let's make it larger. Fix 17. Okay, so what we see here is that actually it looks quite nice. So as sample size increases, for a small sample size, the coefficients so like say here, let me do one more thing. Res review set index time period. Okay, in place. Okay, so let me do this. Now this no frequency information. Yeah, it's fine. And let's do this. Okay, now we have years here on the x-axis. So it used in the values as years. And I mean quarters. So now when we start with the small sample, like we have only a few years, the coefficient estimates change wildly. But then as time goes by, they seem to stabilize, and it's pretty good. So like after some years, we add new data points, and the coefficients are actually, the estimates are quite stable. So there's no evidence that like just eyeballing the estimates of coefficients as we add each quarter, that they at some point change wildly, except for, of course, our 2008 quarter 2 or 3 maybe. So we see here there's this bump here, this trough here. So perhaps I mean, this recursive estimation also tells us that there is something going on here. But the thing is that it's fine before and after. So we can do another test also included here, is so-called plot cum sum, cumulative statistics. It's a very convenient way of doing the estimation. And so what we see here, this is 5% significance interval, and this is the cumulative error. of the estimates as we go along. It's the formula. There is a formula here. No, there's no formula here, but basically they calculate the deviation of residuals from the mean. And for us, what's important, we just look at this cumulative sum of deviations of residuals from the mean, and we want to see if it would go beyond of the 5% bands, these dashed lines, and if it goes, then it's an evidence of structural breaks. So we don't see it stays within the bands. Another related graph to do is sum squared. It's somewhat different. And it also stays within the confidence bands. So seems like we're doing fine. There are no structural breaks. Nevertheless, so statistically, we don't see, except for like eyeballing the coefficients, we see that there is something going on here. So one way to address this issue that, I mean, I didn't know this because when I was preparing for this session, I was working with a little bit different data. So I didn't know that in the Eurostat, I mean, in this Eurozone statistic, there are no structural breaks, because in some other data set, there are structural breaks. But let me do what you could do if you notice structural breaks. So the next step would be, let's suppose I want to somehow address this period. And one super stupid way to do it is to just include a dummy here for this period of, say, after second quarter of 2008 and say till 2012, perhaps quarter one of 2012. So let's do this. We have dummy one if T, say, time. Well, let me say start date is equal to time 1741 plus the offset quarter end. And let's go till perhaps 2000, I don't know, 11 quarter four. Oh, sorry. PD, time. Oh, no PD. And day. And day. Now 0 for T in the index. Okay, so let's see, just to markdown. So I'm just printing out the whole data frame. So it starts 1997 quarter, goes 0, 0, 0, dummy is 0, up until quarter 2, quarter 1, right, quarter 1. And then let's say actually quarter 2. Let's do quarter 2. And then it would go up until quarter 4 of 2011, and then again 0. So I will have this dummy variable for this period, maybe capturing the fact that there is something going on here. Maybe in other data sets it will be more pronounced. I think they have pictures here for more pronounced. Yeah, quantity theory of money. Let's see. Here, like, they have some regression where there is the structural break during this period, whatever is 1980 to 2000. So you can have in some situations structural breaks, so the parameters, the model changes drastically inside this period, and then somehow it goes back. So we don't observe this, but we will do it anyway. We will use the dummies. Okay, we created a dummy, and now we can run mod like this dummy, more or less from formula. PDP, CCI, ICI, LPI in harmonized index of consumer prices, and dummy data yield is equal to mod it summary. What did I do wrong? Summary. Okay, so let's see. Well, not really significant. Didn't really change much. Okay, so including dummy didn't help, but sometimes it helps. But okay, perhaps let's do it for this period. Not really. So it doesn't really matter. Perhaps I will find some data set for which it would matter, and then it would be seen clearly. But this is the usual way to deal. You would include a dummy around the period. This is one way. This kind of captures the level effect, but you can also interact this dummy with some variables like inflation, say. I included the interaction term. Also not really significant. Maybe IPI. No, nothing is significant. Okay, doesn't really matter. But these are the ways how you can include dummies, do interactions, and basically by including the interaction term, you kind of estimating in effect a different model for the period of that dummy. Okay, so that kind of finishes the part of the model selection, diagnostics. We see that somehow it turned out this model is quite good. I guess I can make it worse, but I don't want to go back and make it worse by suppose if I dealt, let me restart and do it not in gross but in levels. So I will not convert to quarterly, but I'm not going to convert to gross rates. Let's see how that looks. Now, if we do it not in gross rates, okay, we have everything becomes significant. Interesting. We can say do this. Now we definitely have heteroskedasticity. Not surprising. So like here, it's one level. Here is much higher. So we have heteroskedasticity, but we can check this more formally as what we were doing. So the Breuer-Godfrey-Pagan test. Now p-value is super low, and so probability of H0 is low, and basically we reject the homoskedasticity, and Y test I'm pretty sure will reject as well. Yes. And then we can plot the residuals. Aha, now they look serially correlated, because this is what we expect from a serially correlated data. It goes down, up, and like not like wildly, but like in some kind of patterns, in waves. And then we can do the Darwin-Watt statistic, and now it's very close to zero, which signals us positive correlation in the data. Then this is a second order correlation of Breuer-Godfrey test. Also, we now get definitely second order correlation, maybe even third order. Even a third order. So we have serial correlation. Let's see the normality of errors. Normalities doesn't look well. It's not normal. It's like feels like uniform. Let's see the test of Barrow test. So now H0 is normality, probability is high, yes. So normality we don't reject, but we're definitely dealing with serial correlation. And then I'm not sure this is a good test if we have serial correlation, actually. Then let's do the parameter stability. Now there's definitely a structural break, but I'm pretty sure there will be structural breaks like at any point where, let's say, let's choose just 2000 quarter one. Oh no, actually no. But definitely now it's signal structural break. Let's do our coefficients. Now we see that the coefficient estimates change a lot. Like here is like down, up, not stabilizing. The same here. So definitely we're dealing with something not nice here. Let's see how this looks. So from 2012, we're definitely dealing with a structural break. And here, well, this test, these are somewhat different tests. This test tells us that something is happening between 2004 and 2012. But economic intuition tells us that around 2008, something was happening. And definitely we see it on the coefficient estimates as well. So now we can, if we add dummies, say from Q1 2008, well, no, Q2 till say 2012. I'm pretty sure it will be significant now. Yes, it becomes significant. And now it's kind of a different model where the dummy is significant, and you can use this model for forecasting. And I did this whole reiteration just to show you that when we move to levels instead of gross rates, we start getting all these issues. So perhaps maybe I should have started with the levels model, because it's like everything breaks and all the test tells us that there is a structural break, so the model is not correct. But we probably should have already stopped here and realized that this is a wrong model. And then we saw that there is a heteroskedasticity, and so probably something is not right. That's why I will go back to the model in gross rates, because it looks like it's a right model, not the right model, a good model. And now in like remaining 30 minutes, I will try using it for forecasting. Actually, I did forecasting last time. Now, should I ask you to do the forecasting? Okay, let me do it, and then I will give you an assignment, first assignment for this class, today or tomorrow, to do the same stuff, but with, say, Russian data. Okay, so let's go to forecasting now. Are you with me? Did you get what I was explaining, showing?
Yes.
Okay, perfect. Is it only one person? Is anyone else following? Thank you, Ekaterina. Okay, now I want to run one thing by you. So you saw, I already showed in the last tutorial how we can do forecasting. And here I want to pause for a second, and before I do any codes, because I did codes already last time. And basically what I want to do now would be just a repetition what I've done last time. But I want to talk about some conceptual things before I repeat the codes. And hopefully these conceptual things would make you understand why I did things last time the way I did. So remember, last time, what I was doing, I was started with some period, like say, let me open here. And so say I started from 2008 or maybe 2004. I forgot which date I started. And then what I was doing, I was estimating quarter by quarter to the data set, estimating the model, and then forecasting several quarters ahead. And then I was calculating, accumulating the squared error. And then I was comparing a couple of models in terms of their accumulated squared errors for several periods ahead forecasts. And these rolling forecasts. Now, one big reason why I was doing this rolling forecast.
Excuse me.
Uh-huh.
Wasn't it expanded forecast?
Yes, sorry, that's expanding window forecast. Yes, I mean, right. So one reason, but that's not my point. Here, I'm rather want to say that you can go two ways on how you want to evaluate your model. So imagine a situation that you are entering this data set from 1997 to 2020 is all you have. And you don't know what's going to happen in the next few years. And you're given this data set and you're told, give me the best model that I can use to forecast the values that follow. And then who forecasts the values the best wins. How would you be selecting the best model? So I talked about this information criteria. That's one thing. Then, but usually, so you use them as a guidance for sure, information criteria, and we will be using them when we will be selecting across the dynamic models as a one way of selecting across dynamic models. And as another way is to use this expanding window forecast, but you can also do something even simpler. You can, like you're told that your model will win if it will be the best in forecasting the next 4 quarters, not 4, 8 quarters after 2020. What you can do to select the best model, you can limit yourself the estimation by 2018, and then use the last 2 years of the data that you have to select the best model that predicts closest to the data, forecast the best in the last 2 years of the data that you have, 2019, 2020. So that's one way to go, and people definitely do this. But this kind of expanding forecast, that is a bit maybe that I was doing last time, where you start not from 2019, you start earlier, and you repeat your exercise several times, and then you calculate the accumulated error. That kind of evaluation of the model using this approach is a bit more in the spirit of what we discussed in the lecture this week, when we talked about optimality of forecasts. Remember, in the lecture, I was talking about this thing that, like say, with the mean squared error, when we forecast, our best forecast under the mean squared error is the mean of the outcome. And that means that when the outcome is realized, we might never hit it. But on average, we will hit it well in terms of its mean. And so how would you capture the best model that performs the best in terms of hitting the mean. You repeat that exercise many times instead of just one time for the last 4 quarters of the data you have. And that's why doing this expanding forecast for many quarters makes sense. Now, you might say, but what about estimating the model, say, up until 2010, and then keeping the model fixed and keep applying this model to the newly arriving data? So then selecting the best model that would be forecasting the data for 2011, 12, and so on for the next 8 years, the best. You can do this. This is also a way to go. So you keep the model, you don't re-estimate the model, you keep it fixed, and you use it to evaluate it for many, many quarters ahead, like 40% of the quarters of your data. That's also one viable approach. In practice, I guess you should experiment with different approaches, and you should think about which one is the best. So let me stop here and just make sure, because I'm talking too much, just make sure that you're following what I'm trying to say.
This approach, when we take the half of our data, fix the model, and try to predict for the rest half, isn't it just, I don't know, the simpler version of expanding window and actually less effective because we
Okay,
don't use all the data?
right. Okay, so the question about less effective. The thing is, it's a fine. There is no theory here, I guess. It's a fine art of how you select the best model. I mean, it's not a coincidence that there are like competitions and for not forecasting in machine learning, but it's just forecasting, if you will. And also, it's not a coincidence that the best forecasters charge a lot of money for their forecasts, because there's an art in forecasting, and it involves many, many things. And so this thing about less or more efficient, it goes to the question of, do you think your model changes or not with time? Because if you think that your model doesn't change with time, but maybe it gets, like, sometimes your data gets some shocks, and that may skew your model, I mean, distort your model, but your model shouldn't be kind of adjusting to these distortions that are coming. Maybe you should keep it fixed and see how it performs and predicting far ahead. And maybe the model that is fixed and performs the best in predicting far into the future is actually the model you want to go with, because maybe you believe that what's happening after some period are maybe unusual events. That's why this dummy approach, that's where this dummy approach might help to capture this unusual event. So maybe just keep your model fixed, see which one performs the best, even given the unusual effects, and go with that model. Because it's like, on the other hand, if you keep re-estimating the model as the data arrives, maybe you are moving the model too much to the big shocks in the data. maybe. But obviously, looking at this stuff here, at this coefficients, we see that the model doesn't change much. So this rolling, probably if we do any of these two exercises, they would probably select similar models as the best ones. So at least, so we're dealing here with one model only. But if we consider different models, like we exclude some insignificant coefficients, let's say if we now consider the model where we drop this one, which wasn't significant, and estimate it. So actually, it looks very similar, except for the consumer price index. Now it kind of, it was more stable, I believe, before. I see. What's the ICI, industrial confidence indicator? Did it look better? No, it looked similar. Okay. So, but maybe we want, yeah, usually we want to go with more parsimonious models. So if it's not significant, maybe we should drop it. And then compare which model behaves better on both this kind of expanding forecasting with re-estimation of the model and fixed model and estimation many horizons ahead. And probably both ways would select the more parsimonious model. Okay, let us do this. So enough talking. I just talked a bit that there might be reasons sometimes to do the model evaluation in this way. You fix the model and then estimate it on many horizons ahead. Another way is fix the model on estimate the model on the full data set that you have, except for the last 8 quarters, and then compare performance on models only on 8 quarters, which kind of a bit goes against the spirit of forecasting. But still, people do this. I don't like it personally, but maybe that eventually is the thing that gives you the best performance. Then you might go with it. Okay, so let's do. Again, we can say start. Say the training is the you time period. Frame the threshold. Say let's say to some quarter one. Nope. I think, yeah. Like this. Okay. then what we do, we just simply estimate our model. And now we use it for prediction. Let's see. What's happening? Why it's taking so long? Hey. That's weird. Hmm. Uh-oh. No. Doesn't work. I think I lost connection. Mhm. Okay. Okay. Connection was lost. So we are back and say now let's predict. So exogenous. So let's do this. First. I have it here, right? Ah, like this. No? Ah, no. Ah, CCI. Okay. And we can actually even plot it. Um, So this is our prediction. And we can calculate this in, say 1. It would be this number, let's put there y hat the best GDP. Nope. Okay, so that would be 1, and let's say we can do the whole thing now here. Probably that's not the best way to do mix formula and non-formula, but okay, no more time, let's do it this way. Okay, let me actually change it a bit. Just yeah, just edit constant here to have it as my column. Well, or intercept. Okay. Not much time left. Okay, let's do it here. Just now the best. Okay. So I just rewrote it in a more generic way where we can now experiment with changing this part and seeing how different models perform in terms of, say, let's call it um, um, okay, perfect. Now we can compare a couple of models. Model 1 columns, model 1, model 2 columns. Say we drop this one, which was not significant. Let's see how it performs. Model 1 columns, model 2 columns. Oops. Aha, you see, the second, more parsimonious model performs better. Uh, did I lose you? Was I doing it too fast, not explaining what's going on?
Well, you just built a function, and now you can write the set of the variables and
Yeah,
compare the errors, well, mean square errors.
perfect. Okay, understood. Now, so this was one way of doing it. I just estimated the model. It's not an expanding estimation, right? It's a static. And I want to do the same for expanding, but I actually, there is no time, but I did it last time. So you can just take pieces of what I did last time and do it and compare it. And I will give you a home assignment on that. Using the repeat everything I did, but using Russian data. Now, the last thing I want to say, like I will get just 1 minute from you, and I have a question. Why do you think this smaller model performs better? it has a lower squared error.
From the statistical point of view, if we include some extra variable which doesn't, which is insignificant, we just receive noise. And this noise is reflected in higher mean square error. That's why the second model has less mean square error, less noise.
It's kind of, but it's not kind of. So, let me throw it here. And this is a very, you're not supposed to know it like very well. You said it kind of in the way, but not exactly. And this is a very important point of machine learning. And we are going to talk about it during lectures, but I just wanted to have it like as a first run of it. Wanted to draw your attention to this fact that a smaller model can have a better performance. And the explanation is that when you add more variables, you kind of, it's not the fact that you are introducing the noise in the way you described, because, you know, in terms of R squared, this model would be better. And in that sense, introducing the noise helps to capture other noise in the model. So in sample fit, definitely is better for this model. That other model would explain more that first bigger model would explain more variation in the data than in sample than the second model. To say it in a different way, adding additional noise helps to explain the existed noise no matter what, even if marginally it helps. But once you introduce this noise, the model, you're kind of trying to explain something with that noise, and you're wasting or putting some weight, some explanatory power on that noise, while there shouldn't be. And so when you go to the out of sample forecasting, that noise distorts the forecast. And this is almost what you said, but I wanted to make this distinction between in sample and out of sample. Because in sample, adding noise always helps, but out sample, it might not help. And then that kind of goes into another phenomenon called bias variance trade-off, which we are going to discuss in the lecture on this Tuesday. Okay, I'm done for today, and I will ask you to do everything I did, but using the Russian data, and then find me the best model and show me your forecasts. And you will be working in groups, the ones that you self-assigned during the first lecture.
You will send us the details, right?
Yeah, I will send you the details, right? And I will do it either tomorrow or on Monday.
And we'll have about a week or so.
Yeah, you will have a week, because we need to have a few assignments, and it's like almost end of November, and it's a requirement of the school that you need to have a few assignments.
Yes, okay.
All right.
Thank you for this study session. Goodbye.
Thank you. Goodbye.
Bye.